Today's talk is going to be about general science and a bit about standard model, general relativity, and a bit cosmology, so Newtonian physics, these sort of things. And it's going to be non-technical. I will try to avoid technicality. And so let's start with this notion of standard model. So physicists and scientists, and also many people, philosophers, etc., they always asked how how the world is viewed and what is it made out of, etc., or what holds everything together. And so is this world that we live in, is it real? So, and the answers to these questions are tested mainly, especially in the last century, experimentally, but beforehand, so it was a bit hard to test them. So, and so all the known matter particles that we know of, they're composites of quarks and also leptons, and they interact by exchanging force carrier particles. So I will just now show it pictorially about the standard model, and then I will try to explain what each of these particles are and how they are related to other sciences. So let's call this SM standard model. Yeah. And it comes say in three packages, like these particles. So this is like one package kind of thing, and then this is another, and there's another one here. Okay. So let's start with the top one. So let's do this. So this is like family of particles. One family is here, and one family here, another family here. It's like you can also see it as like English, Irish, Scottish kind of thing. So they have all their own characteristics. That's why we put them together, because they share common traits. And so let's start with the quarks. And so quarks are, do you know any quark names? Or do you know what quark is?
No.
Top
Yes.
quark.
No, what is it?
It's the particle that protons and neutrons are made of.
Okay, good point. So, so proton and neutron, we said. As we know that an atom is made out of three fundamental particles that we know of, and they are electron, proton, and neutron. So this shows that electron is negatively charged and positively charged, and neutron is just neutral. And I will just draw schematically just an atom. So let's draw it like that. I mean, this is very bad drawing, okay? So in real life it is not like this at all. It's just to make it clear. So this bit in the middle, what we call is nucleus, okay? And whatever inside the nucleus we call nucleons. Okay, so let's call nucleons. And inside we have protons and neutrons. Okay? And outside we have electrons, like they orbit the nucleus from outside. Okay? And similarly, how planets go around the sun, but not exactly in the same manner. And the distance between electrons and the nucleus is really, really far away. So there's a huge, massive space from the nucleus cloud here, and from also electron cloud. This, like the reason I said cloud, because we cannot really see them. They look fuzzy, even with the best electron microscopes. So as we can see, so there's proton and neutron in the nucleus, and there's electron outside. And electrons also come in shells, depending on the structure of the elements, and how big they are and this, that. So it starts from hydrogen till up to iron, 56. So it starts from hydrogen, goes up to iron. 56 is the, okay, so 1, 56. It's just, this one, we call it also proton, and it is the most basic of atoms. And they are all made up inside the stars, okay? And the last element that is being made up is iron, and that is the most stable element, and it's being manufactured in big, like big giant stars. So, for example, our sun cannot manufacture iron. So what happens? Like all the elements in between, they are being manufactured throughout the evolution process of a star, and then with supernova, the star implodes and explodes, scattered around and all that, so it becomes like a nebula, and then all these like particles of let's say iron or other elements, they start like moving in space, and then some of them they come to Earth, etc. And then so it's a long process, but then still we are getting like iron particles through the atmosphere, okay, and it is very like necessary for our survival. Why? For example, we have doctors in the audience, and you know that iron is very important in hemoglobin, which is situated especially in red blood cells. And as we know, the red blood cells also, they don't have nucleus. It's the only like cell that doesn't have nucleus. So it has increased like capacity of attaching oxygen molecules, and it helps, like it facilitates our breathing. So you see how everything is like related. So in this example we can see, and all these, they have nucleus, and then they have like protons and like neutrons inside the nucleus. And the hydrogen is also called like proton because it has just one proton in the nucleus. So later on we found out that protons and neutrons, they are made up of something called quarks. They're like more like smaller particles. Yeah?
So an atom
Yes.
is composed of electron, proton, and neutron.
Yep.
Okay, could you just write that?
Okay. So should I write it in?
Just equals or something.
Oh, okay.
Yeah.
Okay. Okay. Let's get back. Okay. So atoms are composed of electrons, protons, and neutrons. And electrons and protons, they are charged.
Mm-hmm.
So when they are charged, what we call this is electrically charged. Okay, we will see later on that that charge plays a key role in electromagnetic force and electromagnetic interactions. That's what this electron is kind of like bound to this nucleus. So it does not like shoot off or drift away from here.
Mm.
And so that charge, because it's negatively charged and this one positively charged, so opposite charges they attract. So that's why like
Okay.
it's like a kind of, so it's orbiting or
Yeah.
yes.
You stopped at iron 56, is that right?
Yeah,
Isn't
that's
there
right.
more elements in the periodic table?
Now after this, they're all like radioactive elements. So this is the like essence
Mm-hmm.
of all the elements. So we also have, we show in the graphs that like, for example, so it goes like, kind of like this. So it starts from here, like with, hydrogen, and then, goes like beryllium, helium, etc. So it goes all the way, like, up to here, iron and nickel. Okay? And then the radioactive elements start. And so iron is the most stable of all the elements. And yes.
So what's the relevance of the elements and the atoms? They're composed of atoms.
Yes. So, for example, let's say, give an example. Say, hydrogen is like there's one proton here, and then let's say there's an electron orbiting around. Okay, and then next in the periodic table, say helium.
Mm-hmm.
So helium has proton, and so it has two. So you have two electrons. Okay.
So that the increase in the proton makes the difference. In the
Yes,
elements.
and a proton number and electron number, they have to be equal.
Oh, so 2, 2.
Yes.
Okay. Interesting.
So proton numbers, like so 2 pluses, 2 minuses, kind of thing, so equal. So it grows like this, and then you get another shell. You put another electron. You can put like proton and then a neutron, etc. So and then it gives you, let's say, beryllium, so hydrogen, and helium, and then beryllium, and then it goes like lithium, carbon, oxygen, all the way, up to iron as like stable elements, and then the rest is about like radioactive elements. For example, uranium is one of the radioactive elements. So we will talk about these in a bit more detail. So why I wanted to mention this, because how this is related to that. So because first we did not discover quarks. First we discovered, there's atom, and then there's more to atom. What is it? Okay, you found like electron, and then proton and neutrons, and then so is there more to it? So what is protons made out of? So protons, they are made out of quarks, and then particles, fundamental particles like electrons, they are on like over here, so they are called leptons. Okay, and then here we call something like these are called bosons. So these are gauge bosons. So we have, say, photon, and then we have W plus minus Z and Higgs boson, and also we have mesons here. So I'll explain now. So these are force carrying particles. What I mean by that, for example, quarks, say let's take proton. So proton is made out of quarks. So let's say three quarks, say come together and make up the proton. So then we ask the question, so how do these quarks, they are like glued together to one another? Why can't like they separate? So the force which holds them together there, so see this, because we cannot find quarks individually in the universe. They're very social particles, okay? So they have to be together. And the force which holds them together is what we call strong force. And so that strong force is mediated by force carrying particles, and we call them gluons. Okay, so so we have, let me put it here, say G. So this is gluons. So it's responsible of holding these quarks together. So, and it's a gauge boson.
So,
Yes.
can we see these things?
Can you see these things? Okay. You cannot, with your eyes, you cannot see them. But what you see is when you do like collisions, let's say, you know, hadrons, when they collide, you see that there are lots of like small particles are being produced, and the production of all these particles are displayed as like say, you know, I'm just giving an analogy, like on a like a plate, and all their paths. So this is as if like let's say, you know, let's take something very fragile, okay, and then just smash it. So when we smash it, it's gonna be smashed into lots of like parts, and all these parts, they will be scattered, you know, from the ground to the ground. So what we see is the path of each these parts, yeah, they are following a certain like trajectory, in this way, that way, etc. We can follow the paths and of these particles and their velocity, and so then we can deduce like their mass, and then we can come to a conclusion that okay, so this is different than this one, and this has different charge, because also we have like other conditions. For example, we put electromagnetic field in the vicinity where the collisions happen. So electromagnetic field can really affect a certain particle which has a positive charge, and then there's another particle might have negative charge, and if it has like a non-interacting particle, like for example photon, it doesn't have any like charge, so it will not get affected by a charge field, so it's going to go kind of straight. So if it is, let's say, you know, if it has like a positive charge, it may go left, and negative it may go right, so through this.
So
Otherwise
it's the effects.
yes,
Yeah.
but the effects are being displayed on computers, and also like before computers were properly developed, they were displayed on like bubble chambers, what we call, and so yeah, that's what. And the same thing about like all these, you know, cosmic particles that come through the atmosphere, and we have like certain like tools which detect them. So we do not really see them, but we just see the effects like them.
Thanks.
Okay. And so quarks and leptons, we said, and then we have like force-carrying particles. Okay, we call them gauge bosons, and these, they are called fermions. Okay, so like the whole this one is called fermions, and the reason they are called bosons and fermions is because there's something called a Pauli exclusion principle. Okay, so and fermions, they have so they obey this Pauli exclusion principle, and bosons they don't, and so that's why like that's why we call them like fermions and bosons. There's, so but okay, let me not digress and diverge from this. And okay, let's talk about this again in this. So for example, leptons. The most famous lepton that we know is electron, and then we have muon and tau. Okay, and then we have neutrinos. Okay, so neutrinos. So we have electron neutrino, muon neutrino, and tau neutrino. So these are called leptons, and in electromagnetic, yes.
Do leptons make electrons? Is that what?
Yes. So what this means, the electron that you see here,
Yeah.
is
It's
a
composed
fundamental.
of leptons.
It is a lepton.
Oh, it's a
Okay,
lepton.
it's a lepton, and so it's like this. Let's say this guy is John, human, so kind of thing. So it's a,
Okay.
okay, and so these are called leptons.
So quarks actually compose protons, but electrons are leptons.
Exactly.
Yeah.
And and then you have also something called like neutrinos, and so this is, for example, electron neutrino.
Mm-hmm.
They're almost like massless, like a negligible mass.
They've become famous recently, haven't they?
Oh yeah,
neutrinos?
because the scientists they were thinking that neutrinos they would for a while they were the candidates for dark matter. Okay,
Mm.
so but then we realized that actually they cannot be the candidates of dark matter anymore. So we have other candidates like neutralinos and axions and that sort of stuff. So yeah, they are famous and they still do experiments because they have like, this like negligible mass and also they don't have charge, so they do not interact with the matter that much, and then so they just whiz past through the Earth itself, so without interacting anything. Yes.
Can you use that pen?
Okay. Yes. Yes. Sorry.
Or the other black one? I think that one's quite faded.
So okay, so I think this is clear. Okay, so about quarks. So again, as you can see, like what this is called a doublet. Okay, so this like because there are two of them, so it's a doublet. This is a doublet. This is a doublet. Okay, and so the mass of so this is the lightest lepton, and then muon, and then tau. So it goes in that way. So there's a family. So for example, all of these they are charged, and then these are not charged, and they're related. The reason that they are related, for example, when one of them once decays into something else, so it's just they just give out these neutrinos. Okay. So quarks. Yes.
Sorry, just a bit confused. So you're saying
sorry.
electron
Yeah.
is a lepton
Yes.
and it orbits the proton, neutron.
Yeah,
nucleus.
that's right.
So where are these neutrinos? Where are they?
Oh, okay. I will talk
these
about.
are the-
Okay, I will talk about the fundamental like four forces or four interactions that we have. So, what are they? Electromagnetic force. So these charged particles, okay, like electrons and protons, yeah, they are crucial in electromagnetic interactions or in electromagnetic force. Neutrinos, they are very important in what we call something called like weak force, okay, and then there's also strong force. So strong force is responsible for quarks, their binding, okay, and then we have gravity, and gravitational force. It has also its own particles called gravitons. So that's why like this is related. But after like I finish this part, and then I will put it nicely. So what is the first let's say doublet of quarks? Yes. Okay. So we have like up and down. Okay. And then we have strange, charm, and we have top, bottom. Okay. Don't worry about the names. Okay. It's like a horse, donkey, and that sort of stuff. But they come up with funny names. And so what we say, for example, we have something called hadrons, and so protons and neutrons, they are hadrons, and then as you can see, so like three quarks, when they come together, they make up a proton or a neutron. And quarks, they are also charged, but they have fractional charges, like 2/3 and like 1/3 or -1/3. Yes.
Sorry, did you just say that three quarks make a
proton, and
Electron.
also neutron.
A hadron.
Proton and neutron.
Neutron, yeah.
Oh, neutron. Sorry, I thought
Yeah.
you said.
And so, okay. So we have also. Let me make this clear. Okay. Yeah. So we also this we have lots of funny names, but I will try to make. Okay. So hadrons. So we have hadrons, and the hadrons are divided into so baryons and also mesons. Okay. So baryons, they are like 3 quarks coming together. Mesons, 1 quark, one antiquark. Antiquark is like antiparticle. So you have matter, then you have antimatter. For example, electron, which is negatively charged, has a antiparticle which is positively charged, and we call that positron. Okay. The only difference between particle and antiparticle is their charge, their mass and other characteristics. They're all the same. Now the question is, why do we see that in the universe, like it's all like matter kind of thing, and not this is not like antimatter? So why is it that we see things and we feel and all that sort of stuff, everything is made up of like matter and not antimatter? Okay, this is a question for you. Just think about it. What might be the case? Right? And then, so as you can see, so hadrons and so if you read about let's cosmology and how the universe started this that, you will see that there's a term called baryogenesis. Okay, so that says that baryogenesis is when these protons and neutrons started forming at an early universe. So that's where the name comes from. Yeah?
What's the relevance of hadrons? Why are we talking about that now?
Oh, okay, so the reason that we are talking about these hadrons, they are quark particles. Okay, so 3 quarks come together, they make a baryon, proton and neutron, and then 1 quark and 1 antiquark, they come together and they make a meson. And an example of meson is say pi is a meson, or count is a meson, and there are many of them. And that's why I wanted to talk address that, and also I wanted to tell you about antiparticle. So yes.
So we know what baryons do. They make protons, neutrons, nucleus components. What do mesons do? What's their function?
Oh yeah, as I told you, they make up also other particles, and a zoo of particles. They're really like pions, counts, and there are many of them.
But they're not found in nucleus matter.
No. They're mainly decaying particles.
So what do baryons make again?
Oh, baryons are proton and neutron.
Okay, that's the classification.
Yeah, that's the classification. So whenever you read something, an article or this, that, or about the universe, when it says, let's say, baryogenesis, this term, then you will say, okay, so it's talking about when the protons and neutrons started forming. So it's talking about that. So you will be familiar with that sort of terminology.
Okay.
Yes.
So there was a time when matter, there was no atoms. It was only
Exactly, yes.
quarks and leptons.
Yeah. So in cosmology, we have so we start with the Big Bang, and then the inflation happened, and then afterwards we have this era called radiation-dominated universe, and then we have an era called matter-dominated universe, and then now we are in an era of accelerated universe. So all these different eras, we call them epochs, and in these epochs also we have different models. Okay, it's because the mathematics and the physics are really working in a kind of different way, And so nowadays, for example, I mean, we just recently discovered the accelerating universe model, and so also from WMAP, we know that the universe is like Euclidean kind of like flat universe, and so it's like according to the model, so it's like infinite universe kind of thing, but we don't know that for sure unless we determine this lambda, which is the accelerating like constant, or what we call like also dark energy, how it will affect the fate of the universe. Unless we know that, we cannot say whether the universe is going to go eternally, like, you know, infinitely, or it's going to just collapse and this, that. So we cannot, like, so this, yeah. Alright, so this is, I hope this is understood. And then, so as I said, like quarks, for example, they exist in groups, like they are social particles, whereas leptons, they are like solitary particles, so they can be just on their own, going around, etc. And then,
What?
yes.
I just want what sort of differentiates quarks with leptons? Why is there? They seem so fundamental and yet they're different. What composes? What are they comprised of that makes them so different?
Oh, it's just they have certain quantum numbers.
Right.
Okay? Now the quantum numbers. What are quantum numbers? Let's say, you know, their spin. Okay, these are like characteristics. It's if like, you know, we are describing a group of, or a race, let's say, you know, say like race A has got, you know, long nose and, you know, like small head and all that sort of stuff, and then there's another race and you can say like, you know, they're blue and all that sort of stuff. So this is in the same manner. So what we have quantum numbers, and also we have symmetries. We always look for symmetries, and these symmetries, they are always like the same. It's as if like, you know, they're like identity cards of these particles. So we say, for example, all the quarks, yeah, they have fractional charges. Like I said, like, you know, 1/3 or -2/3. They cannot be on their own, for example. They have to be in groups. They are being affected by gluons, which is the like you know, force-carrying particle. So and some other stuff. So that's why like we say, aha, you know. So they are all from like one group or one family. And then when we talk about like electron, muon, tau, then we say, okay, they're all like negatively charged, okay, with like -1 or something. And then like neutrinos, they are not charged, but you know, when like so in decay processes, like we understand that, so they're related, etc. So, and same with when it comes to like force-carrying particles. So we have here W plus and minus and Z gauge bosons. So they are responsible of weak force, and then with this G here is gluon, responsible over strong force. And then we have photon. Photon is responsible of electromagnetic force. And then we have something called here Higgs boson. So, and yeah, you heard in the news about that, like God particle and all that sort of stuff. There's nothing to do with like, you know, specifically like this is the specific God particle, this, that. So it's a misnomer, so for publicity, etc. And so have we found Higgs? No, it's not quite sure. Like we are not sure. We need to determine its spin. Okay, for example. So there are certain characteristics of these particles.
Why?
Yes.
Why do they refer to it as a God particle? What's significant?
It's because this physicist Lederman, he wrote a book, and because Higgs. So this was the only particle out of everything else in standard model that we did not observe, okay, at the time. Still, we are not sure. So then, because it is like an elusive particle, and we have been looking for it, because if we find this, then the model will be kind of completed, okay? And then, so this guy, he wrote this book about Higgs boson. So if he calls it Higgs boson, it's not going to attract media attention and marketing and all that sort of stuff. So he said he wanted to call it goddamn particle. Okay, so he's an American guy, so goddamn particle. Then his publisher said, no, you know what, forget about damn, let's call it God particle. So and then from then media took this and blah blah, all that sort of stuff. So it's yeah, so that's why it's called. And yes.
So, do these gauge bosons, they don't form matter, they just carry force, is that correct?
No, if they don't, if they do not exist, then the matter will not form.
So is that why they call the Higgs boson the God particle, because it gives
No,
mass?
no, it's just, look, Higgs boson gives mass to certain particles, okay? But it just gives about like 5% of the mass. The other 95% of the mass comes from binding energies of these like gluons. Okay? So imagine like, it's just it gives a small amount of mass to certain particles. Okay? So there's a field called Higgs field. And in Higgs field we have Higgs particles. So they interact with certain particles, or they slow down certain particles. And then through this like interaction, the particles like slow down. As if like, let's say, I wanted to ask a question to a teacher who was walking. And then another like student, he saw him as well, and then he came, so we stopped him kind of thing, and now he's walking like slowly. So we are Higgs particles, yeah, making that like big particle, or like famous particle, like slowing down a bit. So then it seems like that the teacher is gaining mass. Okay? But there are others, like for example photons, yeah, it doesn't even get affected by Higgs, it just goes completely not disturbed. So then it seems like then you say, oh okay, so photon is not interacting with things around us. And when your question about like matter, so if you do not have binding energies, like for example gluons, then it will not have matter. Okay, so we need all this stuff. And the funny thing is, all this stuff, it just comprises 4% of the visible universe. And the other like 96%, we have really no clue about, called dark matter and dark energy. And for example, like if we didn't have electromagnetic force, you guys would not be able to like sit in your chairs. You would be just like melt to the ground or something, just collapse. So that's why like it's so significant. Yes.
Could you remind us which are the force-carrying particles? Because you said there's a
These are
strong
force-carrying
force.
particles. Look, photon is an interactive particle in electromagnetism, like between electrons, etc. Gluon is a force-carrying particle between quarks, and so gluons also, they have charge, what we call it colored charge. Okay, it has nothing to do with colors; it's just the name of it. Okay, and then we have a W plus minus and Z bosons. They are important in weak interactions. Okay, and then we have something called Higgs boson. And the Higgs boson is Higgs mechanism is a mechanism where it gives a certain mass to certain particles, but not the whole mass. Just give about like 5% of the mass. 95% of the mass comes from these binding energies of these gluons. And there is a misconception like in the media, and many even like students, like undergraduate students, they don't even know it like properly. So it's a very bad publicity, I would say. They think like, oh, like this Higgs Higgs boson and this it gives the mass to all the particles, etc. Whereas it's just 5% compared to 95% of binding energies. It's nothing, right? But still, like, it is important. Yes.
So basically, what we're studying is all the different energies that are. We're studying forces. This is the forces that bind matter together, isn't it?
Yes, yeah, that's right. Yeah.
Okay. And without any one of these forces being present, then matter as we know it would behave differently.
Definitely, yeah.
Okay.
It's like it's a very delicate balance,
Mm-hmm.
and also we have like things called like structure constants, or like fundamental constants, where these constants have to have like certain values for this matter to interact with them in a very like profound and precise manner.
So these different epochs of what do you call it? Cosmology?
Yes,
Yeah.
like
The different epochs. They're basically mathematicians and physicists' way of describing the history of how matter came into existence. Yeah, different models. Some could be right, some could be accurate, but they're hypotheses. Yeah.
yeah, that's
Not
right. Yeah,
necessarily-
yeah. Like it's like we said like they can be changed, and we don't have like a definite answer.
Okay, so they just they explain it well, but they don't. We can't be absolutely sure that they are.
But all I'm
completely
saying is just look at the percentages. Yeah,
Yeah.
4% makes up about the like visible universe, including like intergalactic gas and dust kind of stuff. 4% of the universe we are kind of aware of. I'm not even telling you, yeah. We do not even understand this 4% completely, right? But this is what I'm talking about, the matter. And the other 96% is dark energy and dark matter,
Mhm.
okay?
That's just a name given to an unknown.
Yeah, because we call them dark because we have no clue. Because
Okay.
only we understand things when there's light. When we detect things, even like in biochemistry, genetics, they all use colors, waves, like spectrography and all that sort of stuff. Spectrometry, like protein, they color the proteins and then they analyze. Like it all depends on colors, waves, basically light.
Light, yeah.
Okay, so when there's no light, there's darkness.
So
So that's why you call it like dark matter, okay, or dark energy, because we have no clue. But we are working on it. Who knows? So at the moment, like, how can you claim that you know everything, or you know, oh yeah, this is correct and everything is perfect and all that sort of stuff? You cannot say that. Do you understand? So it's just ridiculous if someone tells you that, oh yeah, this is the model and this is true, and the universe will end like this, or universe started like this, and all that sort of stuff. No one can say anything definite. And so, but we are working on it, and it is really an exciting arena, because lots of unanswered questions, and it's just amazing. So this is that. Also, like, I want to give an idea about the scale. Okay, for example, like atom is about 10 to the power of minus 10 meters. Okay, the scaling. So that means after 0 point you have 10 zeros. So that's really small, right? And and then we have for nucleus, okay, we have 10 to the minus 14, okay, meters. And then we have protons, so that's 10 to minus 15, okay. And then we have quarks and electrons, so quarks 10 to the power minus 18 meters, for electrons, and quarks is 10 to the power minus 19. So say so 10 to the power minus 19 meters, and then electrons is like about 10 to the power minus 18 meters. Right, so it's really hard to see them. So that's why like we need the detectors. Yes.
But like, isn't this a bit confusing? Because are these actually particles like balls? They're actually something else, isn't it? Like waves and things. It's complex.
Yeah, it is like we.
Or are they fields or something? Like, it's. Is there any ijma agreement on what is an electron?
No, what do you mean? Like.
Is it agreed upon issue? Like what?
Are you
is-
talking about the how it looks?
Yeah.
No, it's just no.
You can't picture it, can you?
You cannot see it. Just as I told you. No. It's like that's you're asking me like how the universe look like from outside.
Hmm. Yeah.
Exactly.
Okay.
So if because is it electron even? Is it a wave? Or is it a field? Is it a particle? Is it? It's not agreed upon. I don't understand. Is it like that or is it actually?
No, like you look is if you're like it depends. If you're looking at it like from quantum mechanics point of view, then you will take a different view. If you look at from quantum field theory of view, then you will take a different view. If you look at it from classical mechanics point of view, it's different. So it's like.
Which is the correct point of view?
It's not like it's not like there's no like that's why we are striving for. So we want to unify all these forces, okay, and then we can see how things developed from like early universe, and then so what I want to say actually like I want to draw this diagram, which is I think very important, okay, so that you can understand why all this stuff fuss is happening. But make sure like
these are just descriptions for the smallest forms of energy.
what was it?
Yeah, that's the way I'm trying. Is that right, brother?
Sorry?
Basically, what we've got there is codification for the smallest forms of forces that bind matter together.
Yeah, that's right. Yeah, you just yeah.
And
Cool.
there's a few different categories of those forces.
Yep.
Some of them are attractive, some of them are repulsive.
Mm.
And they've got slightly different names.
Yeah.
And they group together. You get threes, twos, ones.
So it's pieces of energy,
Yeah,
families.
yeah, families of the smallest forms that you can describe.
Mm. So these are all fundamental. You're not going to find any quark and divide it into something else now.
Yeah.
We don't know how would you know? It's like these babushka dolls,
Mm.
like from Russia. Same thing.
But it can't go on forever.
Who knows? We don't know. But don't ask me like philosophical questions because we can do that in other time. Then we can talk about some different stuff.
But are scientists at the moment confident that this is the most fundamental form of matter that we can experimentally verify, or energy, or whatever it is?
What do you
Like
mean?
electrons and stuff, like don't people say electron is actually is a composite particle? It has 3 parts,
Mhm.
polon or something.
Okay.
So 'cause the same problem we have in school,
Mhm.
they told us, yeah, proton is fundamental particle.
Mhm.
And
Yeah,
then-
but there is a stage. You see, like you don't. Now, if teaching is an art, right?
Hmm.
So you cannot take a student and then start telling him about the profound or subtleties of the science without giving them like some sort of like simple background.
Hmm.
So there's like talking about like protons are fundamental. It's like it's just slowly they're like making people to not to run away from studying this stuff. So if imagine like if I tell a kid who's doing GCSEs immediately at GCSE level, if I bombard a like kid with all that sort of stuff, immediately, okay, without giving him. You're telling me like to just without showing anyone like what 1, 2, 3 is, just give them and like teach them like integration or something like that. The guy is gonna get like perplexed. Like for example, I say you don't have a physics background, right? So if I write this to you, okay? So what does this mean?
It's upside down
Huh? Now, so what I'm trying to say is, now I need to explain this to you. I need to explain this to you. I need to explain this to you, right? And then I need to also explain this, and then the whole thing together, right? And people will run away. So you just, step by step. And then, when you come to, so it's like you digest the food, right? So that's what this, like everything is all about. And you can see this also in nature as well. And so just I want to finish this by drawing this diagram, which is very important. And then, so we will take a break. So what we call, guys, so I'm sure like you guys heard about Planck, or Planck's constant,
Yeah.
or Plancking time, that.
Planck time.
Yeah, Planck time. So we'll, like, I'll just briefly give you a picture so that this will also make sense. Imagine like, the universe fits the Big Bang model, okay? So it started from a kind of like a point, right? And then in the very like early stages, like microseconds, this, that. So it's gonna like expand, and then the matter will create itself, and then light, etc. So we're gonna be drawing this. So let's say, so it started from here, okay? And do not forget, we talked about like 4 forces. So EM force, strong, weak, and as you can see, you have 3 of them in standard model, but we do not have gravity. Okay. So our aim, so what we are saying is, all these 3 forces, they were unified, okay, at the beginning of the universe, as a single force, with the gravity. For example, with the works of Abdus Salam from Imperial College, so we managed to unify electromagnetism and a weak force, and we call it electroweak theory. And also, as you can see, electricity and magnetism, we unified that as well. Okay, so these gave us like clues. So things can be unified, and everything can be under like kind of unity. So it is going towards towards that direction, and then so the universe started at this point. Okay, what we call is Planck time. Okay, it is like 10 to the power of minus 43 seconds. Yeah, the beginning of the universe. See, this doesn't make like we cannot really fathom it. Okay, and here at this point, all these 4 forces, these are fundamental 4 forces, they were one, a single force. And then a symmetry breaking happens, okay? And then, so let's say this is gravity, goes through that way. Now from here, we get strong, okay? And then from here, we get so this is, let's say, electroweak, and then we get electromagnetism and weak. Now, at present time, we feel the effects of these, okay? But at the beginning, they were all one.
What do you mean by they were one?
it's just like see, let's say let's say, you know, to take an apple, okay? So, and if I cut the apple in 4 pieces, okay, and then I give you 1 piece, and I give this guy 1 piece, and that guy 1 piece, and I take 1 piece, so it's all separated. So what we are saying is, like intuitively we just say, oh, okay, so these are like all parts of something bigger. What is that something bigger? In this analogy, it was an apple. So we say also these forces, actually, they are the manifestations of something which was just one single thing.
And is that what they're trying to call the unifying theory? They're trying
Exactly.
To find, they're trying to find.
That's it. Yes.
What is that?
Yes, this is the
Okay.
unifying theory. So, because if you rewind it back, yeah. So as you can see, these two come here, right? So because these are different epochs, okay? This happened like so it started with 10 to the power minus 43 seconds, and then at this time, as you can see, a strong force separated from electroweak, and then at this time, electromagnetic and weak force, they're separated. And so then we can see clearly that if you rewind it back, it's going to go back to
How do we know that separation? How do we work that?
Okay, we have certain fundamental constants called like structure constants, and in physics, and then we do mathematical calculations.
Yeah.
Like, you know, the way we calculate the age of the universe. So same thing, like through Hubble constant, for example, you can calculate the age of the universe, 13.7 billion, around that, roughly. And then, so same thing, like we have also structure constants for each of these forces. And also we have like fundamental constants, like, you know, for example, let's say G, gravitational constant, okay? And then we have like C, speed of light. We have something called like Planck's constant. And then, so, and then we have other also constants, so we put them all together, you know, we do some calculations. And then we come up with, because they have all units. And for example, we can work through units. We can turn a like distance unit, which is like meters, for example, and then time unit, which is in seconds. We can turn them into one another, like interchangeably. And I will give one example after the break. So this is what I wanted to like tell you, that exactly this is, as you said, like this is what that unification is all about. And the standard model is part of it. And so we want to also incorporate gravity into standard model. So, so this is the next step. That's why, you know, they say like beyond the standard model, where supersymmetry and string theories come into it and play very vital roles. Yes.
So when they were one,
Yes.
these forces, they didn't have their functions in different ways, obviously.
Yeah. Also, I want to say, like, for example, here, the temperature is, for example, is about 10 to the power of 32 Kelvin. Okay, so this is like, so one after one, you have like 32 zeros, Kelvin, right?
Is that hotter than Saudi Arabia?
So it's unbelievable, yeah. So it's just
The kind of humour is almost
yeah, and so it's just craziness. And then, for example, this like over here, like is this like so 10 to the power of minus about like say 40 or something, and then here also inflationary period, that epoch happens. So inflation happened like, you know, very quickly and suddenly, and so because it was so sudden, so it's like exponential kind of expansion, and we describe like exponential expansions with what we call like de Sitter model, And so also at the moment, because the universe is accelerating with this lambda constant, which is a cosmological constant. So cosmological constant at that time of like inflation was also turned on. The funny thing is, like, you know, these like constants of nature, they can be turned on and off at times, and and they have to have like very precise rates, and so that things really work at a certain time, and so as you can see, like these things are happening like at a very early stage of the universe, and then now like this is, let's say, present time, it's like 3 Kelvin like outside in space. So as you can see from where to where, but you know, this is like as I said, like about 13-14 billion years of like evolution rewind. And also the other thing is in the inflation, the universe is like, you know, increased in a very short period of time by about like 10 to the power of 20 or 30. Imagine like something, you are increasing it by this amount. That is very exponential, really, like, again, like unbelievable. But the thing is, like, the inflation theory is first like coined by Guth, and then so it has to be modified as well by Linde as well, and then it's called like a chaotic inflation. Still, like, things are and it solves like a couple of problems, mainly like what we call horizon problem and flatness, flat universe, flatness problem. But still, like, we cannot really show, cannot say 100% that, you know, oh yeah, this is correct perfectly, and this is that, and this is that. So like, you know, this is science, so we're working on it and doing experiments, etc. So we don't know like what's really going on. All we know that we are in a universe which is accelerating. And the funny thing is, imagine, let's say this is the universe. So let's say we are here. So, and then there's, you know, let's say space here, and there's another space here. Further away, further away, the space is accelerating more than this bit here. So as if like, it's like, let's say, you know, let me, like, you know, draw, for example, we are here. Now this one may come here, and then this point here is over here, like, like when it expands, and then it expands again at a like even like more rate. So imagine this, yeah, this is happening, and this has been turned on recently actually, and so it's like unbelievable, and we don't know how it will end, and I think that's enough. And also, yeah, we are talking about like really high energies here, like 10 to the power of 19 GeV kind of thing, whereas when we are like you know, trying to probe into the energy levels of like particles in today's world, so you can say like it's about like 100 GeV to like 10 to the power of -4 eV. So this the like at 100 GeV, like this electroweak force just separated. Yes.
Can you clarify about you mentioned Planck's constant of is that just like a unit of measurement, or and also you know, you said that they had unified they had maybe electroweak force. Is this an observational thing, or is this like mathematical, or
what unified?
No, you said the electroweak force, so you've unified.
Yeah, this experimentally verified, yes, and also mathematically very consistent theory. But we have other problems. So it's not easy work, you see. And hopefully after the break I will talk about a bit about like general relativity and like Minkowski space-time, a bit maybe about black holes. Yes? Okay, let's see.